right, hello everyone. Welcome to our next general meeting. Today we have a very special guest, Dr. Assal, who is a professor here at Cal Poly. He's going to be giving a presentation to you guys today, so let's give him a very warm welcome.
Thank you. So, my name is Hisham Assal, and I used to be a student here. It's just in Hannah, about 35 years ago. Came here as a graduate student, and then went to UCLA, get my PhD, and then came back. And I've been back at Cal Poly since 1996. So it's been like 27 years. I teach at the computer science department. I teach a variety of classes. I teach 101, 202, 203, and then I teach the AI classes 480, 481, and 487. At some point, I taught the discrete math class, but it doesn't have any programming, so I didn't continue with that. All right, so today I want to talk to you about something a little different than what you hear about when you hear AI. So when you hear AI, especially in the media, if you're not a computer science person, you think machine learning immediately. And that's good, but machine learning is not the whole story. And machine learning and deep learning in particular can provide nice results and interesting products. But the big complex systems can benefit a little bit from machine learning, but they require more robust design and reasoning based. Problem with machine learning is that, especially with the generative type of machine learning, is that what's generated is not judged logically. It's just judged based on whether or not it resembles something similar. But logically, that's not always the case. I'm sure you heard the term ChatGPT hallucinations. That means, you ask it to generate something for you and then you read it. You're not familiar with the background, you tend to believe it. But if you do some search on Google for all the statements made in the response, you'll see that maybe half of them have no basis or not even true. So how do you make sure that what you're generating has validity, makes sense? And how do you provide support for it? If you're using BART, which is Google's implementation of ChatGPT, it allows you, there is a Google button on it, you get the statement, it's all search Google for it. Google does the search and then highlights some parts of it and tells you these parts have support in these pages and gives you the link to the pages. And we found no support for these statements, so I don't know why they're there. And then some other statements, they're not even highlighted. So, I want to talk about rule-based systems in multi-agent systems, and I'll talk about those two terms, what we mean. But first, I want to start at the very beginning of artificial intelligence. This is the first paragraph in Alan Turing's paper, Computing Machinery and Intelligence, in the journal Mind in 1950. And the heading for that paragraph is the imitation game. And in the very first sentence, he says, I propose we can build, to consider the question, can we build machines that think, or can machines think? Okay, and then he goes on to describe what he means by that. So when they decided to make a movie about Alan Turing, they called it The Imitation Game. You don't know where the name comes from. And this is an image of the machine they built in the movie. Not sure how close it resembles the actual machine that Alan Turing and his team built towards the end of World War II. to break the German encryption cipher Enigma. And what you're seeing here is a mechanical machine. It's not an electronic machine. And these are all the different settings on it, different characters and numbers and things you can adjust so that you can try all the different combinations to see if you can break the code. And initially, they figured if we do it by machine, we can run through all the different combinations very quickly and we be able to break the code. Good luck. This is a mechanical machine, not an electronic one. So it works not at the speed of light, it works at the speed of gears and mechanical things. So I think one of the motivations for Alan Turing to think about machines as a way of thinking is that what they realized after they built this machine is that we can't just rely on trying all kinds of combinations and going through all of them and figuring out what works. Then somebody in his team, if you watch the movie, if you haven't watched the movie, I suggest you look for it. It's a really interesting movie to watch. But somebody suggested that there is a structure to the messages we intercept from the Germans. Usually they start by something like where it's from, and it ends with something like a command, and there's some kind of a structure. What if we rely on that structure and make assumptions about it so that we're not trying all different combinations, we're trying just a small subset of it, so we have time. The problem with the German Enigma was that they changed the code every day. So they only have 24 hours to figure out what the code is. Because tomorrow they will have to start from scratch. And then they did that, and that's what worked. That's what made this machine ultimately work. So what I like about this story is that we can't just rely on the speed of the machine or the power of the machine to try all kinds of combinations and one will hit. There is knowledge. And if you capture that knowledge and you're able to represent it in a good structured way and structured computable way, then you can go much further and you can do more intelligent work. Are you guys familiar with Dilbert, the engineering comic strip? So here, Dilbert is being asked to try this new machine and apply the Alan Turing test to it. And Dilbert, being the intelligent engineer who's not in management and always has problems with management, asks, well, I'll ask it to write a strategy for our company. So the response comes, our strategy is to visionize quality resources that enhance earnings. Then he says, I'll ask it how to motivate employees. And then the answer comes back, reorganize to improve focus, redefine work as opportunity, and increase it daily. Take time to ask for options, then explain why they're wrong. And then he concludes, it must be a computer because there is no human intelligence. Unless, and then he goes to the next room, nice try, boss. So, so that just shows how difficult it is to actually conduct the Turing test. How do you measure intelligence? So this is in the background. We're not going to dwell much on that. What I want to bring to your attention is where deep learning lies in the general artificial intelligence area. The area of the circle does not represent how much work is involved. The area for artificial intelligence is much bigger than that. Then there's machine learning. There are many techniques for machine learning other than using the neural network. And then deep learning is using neural networks in a specific way, where you have more layers, bigger layers. in terms of number of parameters and so on. Okay. So the first lab assignment I give in my 480 class is that people work with ChatGPT in an area they're familiar with and have them provide some feedback on what they get from ChatGPT, whether it makes sense, whether it's deep enough, not deep enough, or doesn't make sense at all. And that's just to draw your attention to where deep learning fits in artificial intelligence. And as computer science people, you should be able to make that distinction. And when people start saying things like, oh, the AI did this. This is one of the phrases I really hate, whether it's in the movies or in the news. And then we built an AI that does this. Well, what is that? What is the AI that you're talking about? Say a deep learning system, I'll accept that. All right, so in general, let me maybe doing this. There is the general artificial intelligence, at least the parts we focus on here, are the problem-solving techniques that are considered intelligent. Before neural networks became feasible, neural networks are not a new field. It's just that because of the computing power we have now is so great, we can do more complex neural networks. But neural networks started, the research on it started like in the 50s and 60s, and there's more interesting work that was done back then. But there are techniques that, let me point this out. This is search. So there are search techniques, and search is one of the ways you can come up with an intelligent solution. And that depends on how you can represent the problem. If you can represent the problem as a search space, like with a game, simplest one, say the tic-tac-toe, I can say well, here, when I start, I have 9 places I can place my first X. And then after that, I have 8 places for the O, and then I can build a tree that represents all the possible moves in tic-tac-toe, and then at the bottom will be the nodes that represent either a win for X, a win for O, or a draw. Right, so you can do search through some search space, and then maybe guided by some utility function that would explain the value of one path or one choice, and provide this utility function represents the knowledge of the quality of a solution. And there are other more advanced ways of doing search. For example, constraint-based, you can represent your problem as a set of variables with constraints across them. Every variable can have values from a given domain. And then the solution is to find an assignment for all the variables from their domains that would make all the constraints satisfied. So the constraints now represent the knowledge in that domain. And by trying to find the combination of values, there are techniques to minimize the amount of trying out values. So you don't want to try all the values in all the domains. This will be exhaustive search, but the constraints give you some guidance on which values are more likely to keep the constraints satisfied. The second part here is reasoning, and this is where you use logic. And we study logic as a symbolic manipulation of information, and we try to come up with inference mechanisms based on logic. The logic you're most familiar with is what we use in any programming language, the AND and the OR connectors. there are more connectors than that. There's the if then and the if and only if. And those can give you more inference ways to represent a problem and work with it. Then we can build inference mechanisms that are abstract. And then depending on the problem, we can define the problem in terms of logical statements and then use the inference mechanism to generate more statements based on the existing ones. And then the third one here is knowledge representation. This is a way of capturing knowledge from a certain domain and putting it in a structure that allows us to compute with it. This is what we teach in 481, knowledge-based systems. You have to have a knowledge mechanism to represent knowledge in a given domain, and then you have a system to work with that knowledge. You can think of it as data structures on steroids, or sometimes I like to call it smart data structures, because you can apply inference to the structures you build with the representations. And then you have this machine learning stuff where you have different ways of doing learning. You have decision trees. You have the regular neural networks, artificial neural networks, we used to call them. And you have the deep learning, which is still neural networks, but on a deeper level, many more layers, and each layer is many more parameters, so that you can have a more extensive representation of a problem. When I mentioned something I should have mentioned in the beginning, intelligence relies on large amounts of data. Intelligence is not just a set of techniques you apply to any set of data, small or big, but you have to have a lot of data, and then you work it into information, which is related items of data, and then you work that into knowledge, which is sometimes called actionable information. So once you have a good knowledge representation, here you can apply the inference and create more knowledge based on that. Sorry. So what we need to add, in my view, what we need to add to machine learning systems today is some kind of semantic modeling. When you look at images, for example, and you're building a machine learning system to recognize certain objects in images, that's all based on the image structure. It's all a set of pixels, and then the different layers in a system will give you different representations, like if you're looking for cats in images, and it will get the different parts of a cat's face, the ears, the nose, the eyes, throughout the layers, and does all the transformations for it, so whatever cat face may appear in the image. But there's no reason. And if we apply some semantic modeling, so here we have ontologies here, and other structures, the flowers and physical data. We apply some semantic modeling that allows reasoning to machine learning. I think we can go further. So this part is the part I'm working on right now for my own research. All right, so we started by saying, well, talking about agent-based systems. So what are agent-based systems? What's an agent? An agent, by definition, is someone who acts on your behalf, right? If you say, well, I have a real estate agent, that's someone who does the real estate needs that you have. You want to buy a house, sell a house, or find something, then that's the agent. You say, well, my agent, if you're a speaker or an actor or something, so my agent got me this job, there's someone who's acting on your behalf. So to borrow that term, an agent, a software agent is a component, a software component that acts on the user's behalf. And it has to be autonomous, meaning that you don't start it or you don't ask it all the time, go do this, go do that. It has some interest, which is the user's interest, and it's monitoring an environment, so it's embedded in that environment, and it's monitoring that environment continuously. And as the environment changes, new data comes in or data gets changed, it takes the opportunity. If it can do something with the new data, then it will take that opportunity to produce some results, maybe a decision, maybe a recommendation, maybe just adding new data based on the ones added to it, and so on. So that's what an agent is. So an agent perceives the environment, so it must have senses. And we're talking about general agent-based systems. So this may be robots or maybe just software embedded in some existing software. There are two parts where there are the sensors and then there are the percepts. The actuators. The percepts are the pieces of information that come through the sensors. And then if the information is enough, then it can affect that environment by making a change or creating new information and putting it into the environment through a general term actuated sphere, which is not necessarily something that moves, but if it's software, then it can just put more information into the environment. So you look at a human as an agent, there's sensors are what we all know, the five senses, the eyes, the ears, the taste buds, skin, and so on. And then the actuators are the things we affect change in the environment, the hands and the fingers and legs and mouth, all of that. You look at a robot, you have all the sensors, camera and sometimes lidars and all kinds of sensors to perceive the environment. So if you're sending a robot to go into this room and pick up something and go back out, there are two ways you can do that. You can redraw a map of this room and give it a path to walk through it. But if things changed, like if you changed, so I want to pick up my phone, and if I change the location of my phone, I won't be able to find that. Or you can give it all the sensors to perceive the environment, so it's looking for it. Oh, I have an image of this object, where is it? And scans the environment. When it finds it, walks towards it, so it's not walking a prescribed path, and then picks that up and finds its way out. Right? And then software agents are components. So you don't build an agent as the full system. You build an agent as a component of a system, as an existing system. So the input to your component, your agent, this is the sensors. This is how you get information. So there are different techniques for doing that. That may be subscription, that may be pulling or pushing information. The environment may be the internet or maybe just a fixed environment. And then the output, whatever your agent does and puts back in the environment, is the action, and that's done through the components that do that in the agent are called the actuators. So important thing is you have some kind of an environment that you don't necessarily design. This may be an existing environment, and then you just run one of these or more. So multi-agent is where you have multiple of this agent all accessing the same environment and all putting changes in it. Which you can, if you think about it, can be really a complex system. What if the information coming from another agent triggers my agent? How do I respond to that? What if I said, oh, you should go out this door, and the other agent said, no, you should go out this one? What should they do? The whole environment. So there may be conflict. How do you deal with that? So that's something you want to think about. There are many types of agent. The simple reflex agent is one of the simplest architectures for an agent. Sometimes it's even implemented with a table. You get this, then you do this. Or maybe if you have, like for diagnostic systems, if you have a headache and a fever and a runny nose, then you have the flu. And or maybe you should take Tylenol or Advil. So that's a simple reflex agent. A more complex agent requires a model of the world, and the model is not comprehensive. So it's a partial model only for the interest of this given agent. When you want an agent to do something, what information is needed from this environment so that this agent can do the work. Sometimes you can also add a goal. So it's not just responding to changes in information in the environment, but also I have a goal here. Does the information I get from the environment with the actions I know how to perform get me closer to the goal? Or if the information gives me options, which option gets me closer to my goal? And that's the action. That's how I decide on which action to take. All right. Sometimes instead of a goal, you have utility. So how good is this action? And this utility, as I mentioned when we talked about search, it represents the knowledge. What do you mean this action is better than this? That's in terms of the knowledge I have about the problem. So for the diagnosis problem again, if you have the flu and I suggest some antibiotic, is that the best solution? Or how bad is the flu? Would just fever reducers work well enough for you? Antibiotics have some side effects, or if you have other problems like diabetes or something else, the antibiotic may not work well with you. So what is the best solution or a good solution for this? All right. With agents, you can add a learning component. So let's say you want to have an agent that plays a game and it's in an environment where other players place their agents, and you want to see how well your agent does. So you would have a learning component which has a critic that gives you some feedback on how good a move is, or what the information, the current information in the environment mean. And then you have a learning element. So, well, for this kind of information, I want to maybe I tried something before and it didn't give me a good result, didn't give me a winning hand, for example, or a winning position. Then maybe I'll try something else, and then record that. All right. So in general, you can have a knowledge-based agent. And this is where logic comes in. The general structure of a knowledge-based agent here is that we have a knowledge base, which has some kind of representation of your domain. And the knowledge base gets percepts, which is information received from the environment. And then there are two things you can do with the knowledge base. You can ask, so you get information from it, or you can tell, which means you put information into the knowledge base. But what you want to get out of it is an action here. So first you get the percepts, add them to the knowledge base here, and then ask it for an action. And then you tell it that you're going to perform this action because this may change the information in the environment. Okay. But with doing that, we have to make sure that our representation reflects the real world, as close as possible to the real world. And when we have a sentence that is used to provide or to produce another sentence, the sentence is in the structure of this representation, and it reflects some aspect of the real world. Right? So that's the semantics of this sentence. When it generates another sentence, we say entails. This is a term in logic, which means this sentence is produced from this sentence and maybe from other sentences as well. So the new sentence must also reflect some aspect of the real. So we have to be careful when we're trying to model part of the real world so that our sentences make sense and our conclusions also make sense. All right, so that brings us to logic. How do we work with logic? The simplest form of propositional logic is where you represent every statement with one letter or a group of letters, and then you apply the different connectives. You know about the and the or and how they affect the root value of the single propositions. There's also the if then and if and only if, and they work a little differently. For the if then, it's more relaxed than the if and only if. The if then, if the left-hand side, if the premise is true, then we can look at the consequence and see whether it's true or false. So if the premise is true, and then the right-hand side, the consequence is true, then the statement is true. The premise is true, the right-hand side, the consequence is false, then the statement is false. But if the left-hand side is false to begin with, then it doesn't matter. The statement is still true. Right? Or if and only if, that's different. It's if the right-hand side is true and the left-hand side is true, then the statement is true. But if the left-hand side is false and the right-hand side is true, then the statement is false. All right. So it's a little bit more restrictive. As you can see here, it's true here. They differ only on this one, which is the left-hand side is false, the right-hand side is true. In the case of if then, that makes the statement true. In the case of if and only if, makes it false. The problem with propositional logic is simple, but it cannot represent large sets of data. So if I want to say everyone here is a computer science student, then I would have to have as many propositions, one for each one in the room. But if I just want to say everyone here is in computer science, then I would need to use predicate logic. With predicate logic, we use a function or a predicate. A predicate is a function that returns true or false. So with that, I can also use variables. So I can have the predicate, for example, be a student in computer science, and then say X, where X belongs to a set of all people in this room, or all people in computer science, or whatever the set might be. Right. So now I can work with variables. I can have one relation or one predicate describing a whole set of data instead of one statement for each element in that set. And then because of that, I can use quantifiers, one that says for all, so I can apply some relation to every element in the set, or I can use that exists to say there's at least one element in the set that satisfies some conditions. All right. So now, given this structure, whether on the propositional logic or the predicate logic, I can create some inference rules. So if I say if A, then B, and I know that A is true, and I know that the whole statement, if A, then B is true, then what conclusion do I make about B? What is the value of B? So given the inference rules I presented earlier, that means then B has to be true. I work it backwards a little bit. So there are a number of inference rules that can be extracted and implemented in the abstract. And then you can supply it with data and it will tell you what is true and what is false. So using this, I should mention here that the first, what was called an expert system, this term is not used anymore, but that was done in the early 60s at Stanford to diagnose infectious diseases, and it was called MISA. The system was built specifically with the data, so all the data was built in, and all the inference rules like this were mixed with the data. And when the system showed some good results, they started thinking, oh, can we separate the inference from the data and then reuse the inference as an inference engine? And that's what gave rise to the expert systems that were popular in the 80s, all the way until the end of the 80s or maybe the very early 90s. But there are two ways you can write rules, two forms mainly. One is in the if-then format. So on the if part, on the left-hand side, you have the pattern or a number of patterns. And on the right-hand side, you have actions. The patterns are variables, and your actual data gets matched with the variables. But all the patterns in a rule have data to support them, then the actions on the right-hand side of that rule will be excluded. And this one is called forward chaining. The other part, or the other form of writing rules is backward chaining, where you start with a goal. Can I show that this goal, this statement is true? And the way to show that this is true is to show that its sub-goals are all true. So you keep breaking it down into sub-goals until you have facts that support some of your, or all of your sub-goals. Then you start breaking it down a bit like that. That's called backward chaining. So to build a rule-based system, the general architecture you'll need is three things. One is the knowledge base. This is all the statements that represent the knowledge in your domain. We're talking about disease and diagnosis, then these are all the statements that represent this disease has these symptoms or requires this medication and so on. An inference engine, which is a generic inference engine that applies all the inference rules we talked about. And the working memory is the actual data that says, oh, I have these people, this person has these symptoms, the other person has different symptoms, and so on. So that's the general structure. This can be done in many different ways, and maybe there are other components as needed, like an interface, a learning component, or whatever your system is supposed to do. All right. So when you execute a rule, you may create a new state or change an existing state. If you create a new state, this may trigger other rules, and your system keeps running until there is no change or the vast change didn't fit any of the rules. So it will stop waiting for new data or some change. And then you have to have some control structure. Usually that's built in built into the inference engine here. So if your data matches a number of rules, which one will execute first? If that execution invalidates the activation of the previous rules, those should be taken off the inference engine. Any questions? So I want to show you some examples of systems, actual systems we built. So this system, note the date, from 88 to 92. That's when I was a graduate student here. And this system is a CAD system, an existing CAD system, so we didn't build this. And this window is the CAD window, so these are all things can do here. But all of these things here are agents. Each one of them is a different agent. The first one is a database that contains critical knowledge about what you're trying to design here. And then different kinds of agents. Blackboard is for communication. And the GI is a geometry interpreter. The CAD systems back then were just geometry based. You had points on lines, and not even 3D, so you don't have surfaces. You have to have a different component to do that. The geometry interpreter here was a component that would go through and look at the geometry and say, oh, that's a room. And here are the dimensions for this room. That's another room. And here are some openings, a door, and a window, and so on. So that's what this agent did. That's all it did. We have structures, we have lighting, we have sound, we have, I don't know what this is. I can read that. Daylight, I think. And the last one is access. And all of these agents are looking at what is happening in this environment. So the designer is adding a new wall and adding a window, a door, and they go to work. And if something is wrong from their perspective, like the structure guys say, oh, this wall, let's say there's a big window here. Oh, this wall is supposed to be load bearing and have a big window in it. You should have less openings in it to allow it to bear the load. So it would flash and turn red, and then you can click on it and get more information. Why is it upset? Until you have a design that has none of these problems. So everything is fine. So that's a good design from the perspective of these agents. All right, so we have the environment, we have the agents embedded in them. They go to work opportunistically when they get information that fits their purpose, and then they provide feedback in the background. They never interrupt the user, but they just turn red, indicating that they have something to say. And then when the user selects to click on one of them, they get to see what information they have. And that was a design decision from the very beginning. In design environments, you don't want to interrupt the user because the user may already be aware that there is a problem, but they're still working on it. So they don't want to be interrupted. And so here is a problem. So in some cases, a user can do a full design without asking the agents for any additional information because they know what they're doing. And then when they're done, all the agents are happy. Another example here, this is a system I worked on later. I came back to Calpolis from the late 90s and early 2000s. This is port management software for the Navy ships at San Diego. These are the different piers. There are 14 piers. There's some more in this area. And that's the naval port. Every pier has some capabilities, like how much power they can provide, if you can have water supplies on it, if you can do some of the required operations on the ships. And then these are ships here, and they come in different sizes. There's aircraft carriers that are really large. You would take the full pier. Some ships are smaller, so you can have two on the pier, and sometimes they can put them one next to the other, and they would run a cable across one ship to go to the next one. Every ship has requirements. I need water, I need degaussing. Degaussing is getting rid of the static electricity that builds up on the ship as it's moving. I need mail delivery, I need food supplies, this much food, and things like that. And the purpose of the system is to figure out the schedule. So I have these ships coming in the next 3 months. I have some ships already parked here at some of the piers. They're leaving on different days. Where can I park the incoming ships so that I can fulfill all their requirements when they come in? It's a complex problem. We have all these agents on this side. They check different things. They check the schedule. They check the requirements. They check the maintenance schedule. Sometimes the pier is closed because there's maintenance, and so on, so that you place a ship at a certain pier on a certain day. One of those agents will say, that doesn't work for me. I have maintenance on that day. Right? So try to find the schedule for the next 3 months where all the agents are satisfied. Role-based agents, role-based multi-agent systems are used in planning a lot because of the complexity of the problem. You have too many variables, too many requirements, and it's difficult for a human being to just look at all the variables and all the requirements and do the matching. But it's easy for a number of agents. Notice that every agent focuses on just one thing, maintenance schedule. Right? So how it doesn't work for me because I have a maintenance project at that time. That's all. Other agents would say, park this ship here, but I don't have that much electricity, that much power to provide that ship. That's a large ship, requires more power. I don't have that. So the focus is narrow and spread across all the agents, and then they work together. And then you may have, if there is a potential for conflict, you may have an agent dedicated for that. And say, this issue is more important than that, or maybe we can compromise on this, or we'll ask other agents, do you have another solution? Maybe you give me your best solution, but how about the next best? Maybe that works with the next best with the other agent as well. And we'll try to resolve it this way. Not always, you don't always need the conflict resolution thing because it depends on the problem. In many cases, any solution from any agent will work with the others, but in case you need it, then there's a potential for doing that. And then you can have a learning agent. One of those could be a learning agent, which will be collecting information and say, well, maybe the best way to do this is to look at the vast 3 months schedule and repeat that. Maybe if it worked for the last 3 months, we'll repeat that. And maybe there's a change in what ships are coming in. They're not the same, but we'll do it for the most part for the same types of ships, and then we'll just adjust that for the different ships. So that's a learning agent that can provide benefit to the system. What exactly does the agent do? That's up to you. That's up to the designer, and whether it's learning agent, communication agent, or does anything else, scheduling agent, that's another design.